Okay, so sorry. Okay. So now, what is that filter is about, right? So basically, what we are doing here is we have the signal, right? See, remember that whatever is mentioned here, they are all the random process. They are all the random process that you have to understand. Because if I am writing like x of n, it is the signal. It's a function of a discrete signal, right? So that is what we call as the deterministic signal, we can say. Deterministic signal. Right? It is, we know what the signal is about. We know the expression for it, and we know exactly what is being given as an input to this. But as far as this model is considered, this is a stochastic model. It is the random process model. Actually, what we are having this figure is about this random process. It means that your xn here is not a typical signal, deterministic signal. This is basically is a random process. Of course, we assume that random process is wide sense stationary random process, right? So what does it mean? It means that you have a group of signal, right? For example, ECG signal is one such random process. Speech signal having the similar characteristics, right? EEG signal, right? Telecommunication signal, right? Like that. So, say for example, let me consider this example as a speech signal. You are talking, so you have that speech signal now, right? So now you are actually talking with that fan background. You have a background noise. So what actually you get is this corrupted one, right? So this is basically the signal plus noise, right? And remember that whatever is given here, that blue color is a speech signal, right? And you have that noise corrupted. But it is not necessary that the noise is always going to be that high frequency like what I have measured, right? I have shown it is high frequency, but it is not really necessary like that. But some noise is actually getting added with that signal, right? So that is what is a model. Remember that this is one such speech signal, we can say. That is what we said, that it is a random process, right? It is the speech signal. In one time it is going to be like this, right? So in another time when you talk something else, that speech signal is going to be like this, right? So the group of speech signal what actually we collect, right? So those are what we call it as the random process here, right? So this is going to be the random process in this, right? So we are assuming a special random process, what we call it as wide sense stationary random process. We are assuming that the random process what we are collecting is a wide sense stationary random process, right? As you know, how we how to analyze this random process. To analyze this random process, what we do is we tap across the process at two different time instant. For example, let us say, right, say here at t1 and this is t2, we convert the random process. Okay, in this case, instead of having t1, let me put it as n1 and n2, because see, remember that whatever I have drawn, it looks like, I mean, it is a continuous form, but remember that we are discussing in a discrete form. You can actually process. It means that the random process, actually what we are having here is a discrete one. So just for convenient, I am drawing it as a continuous form, right? Remember that. So they are actually the discrete form. Okay, so that you have to be careful, right? So two different time instant, right? So n1 and n2, right? You have the random variable now, xn1 and xn2, right? So this whole speech signal, let us say this is the speech signal, this is the random process, discrete random process to be more precise. This is basically the discrete random process, right? Right? But to analyze this random process xn, what we do is you tap across the process at two different time instant, one at n1, another at what, n2 here, right? So it is not necessarily only 2 points. Of course, what I'm trying to say here is the random process is getting converted into what, the random variable, right? So what does it mean? If I tap across the process at one particular time instant, you get outcome like this. These are all the outcomes. You see that? These are all the outcomes of the random variable. Once you know the outcome of the random variable, it is more convenient for you, because once you know that random variable, we have a characteristics like what? Expectation. I can take expectation. Remember that I can take only expectation for the random variable, not for the random process. This is a important point to understand, right? We can actually take only for the random variable. Of course, I can take it for another point, right? Like expectation of x and 2, right? So this is another random variable. So I can take it for like this, right? So now again, the problem is how many time, I can tap across the process and get a random variable out of it. It will be difficult. It will be difficult to do that. Right? So we go for some sort of assumption, right? Assuming that the random process is stationary, right? One such stationarity, right? What we call this strictly stationary random process means the characteristics will be, identical at every time instant, right? It means that expectation of x n1, if I find, right? So that is going to be what? Same as that of expectation of n2 wherever you tap. Wherever you tap, right? So this expectation is going to be the same, and so on, right? So this is one of the characteristics, and you can have other characteristics, right? You can have a second moment, we can have third moment, we can have a density functions, right? Identical, right? For the random variables obtained from the random process. They are all what we call it as strictly stationary random process. Again, it is difficult to have such random process in practice, and hence actually we are going for a other assumption, which we call it as Whiteson stationary random process. It's a lighter side of random process here. In this case, we say that the random process is said to be Whiteson stationary random process if it satisfies two conditions. One is expectation of xn. Remember that this is a random variable, don't get confused, right? So this is constant. This is constant irrespective of wherever you tap. Irrespective of wherever you tap, this is going to be that constant. That is the first point. The second point is expectation of n plus k xn, right? So that is going to be the function of, right, the difference in the time instance. You are tapping at n plus k and n, and that one we are actually writing it as a gamma x of the difference in the time instant. That is going to be gamma x of k here, right? So difference in the time instant is actually happening here. So this is n plus k here, and this is n. So it depends only on the difference in the time instant and not on the time instant itself. It means that if I have something like expectation of x n1 plus k and then x n1, right? Even in that case, it is also going to be what? Gamma x of k. So what I really mean by this, it depends only on the difference in the time instant, right? And not on the time instance where you tap. Here it is n1 and here it is n, irrespective of wherever you tap, right? If I find out this autocorrelation, this is going to be depends only on the difference in the time instant, right? So the random process is said to be Whiteson stationary random process if it satisfies these two conditions, 1 and 2. Okay, so we are now coming back to the original track. So the problem is you have the speech signal, you are talking, and there is a noise, say for example fan noise, right? So, right, it is going to be there in the background, and you have a signal corrupted here, speech signal corrupted. You need a filter to remove this noise. This is not like, any other filter like high pass filter, low pass filter, right? Band pass filter, right? Where we have that frequency response. We know how that is going to be, that frequency response, right? So it is going to be either, low pass or high pass or, or the band pass, right? We cannot actually do it like this, right? Because, for example, this white noise, the frequency is actually distributed throughout the frequency range, right? The noise is not going to have one particular region. If the noise is in one particular region, then I can look for that study, what type of noise it is and which bandwidth it is occupying. And hence we can actually go for a typical filter design in case of deterministic, then I can remove it. So that is possible. But as this noise, it is totally white. Anytime, any frequency, it is actually having that complete range. We say that it is what we call it as white noise. It is called it as a white noise, right? So in case of deterministic signal, right, we have what is called the Fourier transform, right, to understand about the frequency content of the signal. You know that, right? If I have some signal x of t, then I can comfortably take Fourier transform so that I can know what is that frequency content in it. But if I want to know about the frequency content of the random process, right, then what we have to do? We have to go for what is called the spectral density function, right? So what we have to do is, to know about the frequency content of the random process, you actually have to go for computing this autocorrelation Rx of k, and then take, as it is discrete, you can go for discrete time Fourier transform to get the spectrum, right? This is what we call it as power spectral density, right? In case of continuous case, you have to go for computing this autocorrelation and take the Fourier transform so that you can get the spectral density, which gives you the information about the frequency content of that particular random process X, right? So xt is basically the random process, and then you are actually finding out this autocorrelation and then finding out this Fourier transform, and hence you are able to get the spectral density Sx of f, right? So this is a way how we get the frequency content of the random process. If it is a deterministic, this is a deterministic signal. Every time I just wanted to reinforce that deterministic signal is different, random process is different. This is deterministic signal, and what we are talking here is the random process, which I am representing as x subscript t. This is the random process, right? X of t is a signal, deterministic signal, but xt is a random process, right? Hope this is clear to you. Now, to do this, as I told you, we cannot have a standard filter like high pass, low pass, band pass, and so on. Hence, we need to have a special filter, and that filter is what we call it as Wiener filter, where the transfer function of Wiener filter is statistically obtained. This is h of f, the transfer function of this filter, right? So remember that this filter is actually deterministic filter, deterministic system, right? Not the random number, right? Statistically, we are going to find out the filter coefficient and then we are going to freeze it, right? You can, of course, we are actually discussing this one not in a continuous domain. We are discussing actually the discrete domain, right? So in that case, this filter, what we are considering here is the FIR filter. So you have some filter coefficients available for it, and the number of taps we can fix something like H0, H1 and H2. They are all the filter coefficients. Only 3 tap we are considering. Only 3 tap are considered here, right? Isn't it? 3 tap, right? So now, how to design or how to get these filter coefficients? How to get this filter coefficients, right? And here Xn is the speech signal. What that is the example what we are having. Wn is the white noise, and we are having the summed up Yn, and we have a filter, and we are getting this. Filter is actually predicting your Xn as Xn cap. It is predicting as what? Xn cap, right? And originally it is Xn, and you have this Xn cap, right? And you have this difference, and that is given as what? The error, right? And this error is helpful, right, in designing this filter coefficient, right? So our goal is to find out these filter coefficients that such that this error is getting minimized, right? So that is the way, right, how we do the Wiener filter design, right? So we discussed, of course, you might have seen this one in the video, this FIR filter, how we can actually design this, right? So quickly we can have a outline of what you had seen in a video. Yn is basically Xn plus Wn, right? So remember that Wn is the white noise. The white noise means it is having some statistical characteristics like this, Rw of 0. I mean, otherwise I'll put it as Rw of k, which is expectation of Wn plus k, Wn, right? So this is the autocorrelation. As I know that it is Whiteson stationary random process, so it depends upon the difference in the time instant. And for the white noise, this autocorrelation is going to be the impulse. It is going to be the impulse. At k equal to 0, you are going to have the value as 1. For all other k's, the values are going to be 0. This is one characteristics, right? And then, of course, the equivalent characteristic is, if I take that Fourier transform, in fact, it is discrete. So you have to take discrete time Fourier transform. In that case, your spectral density, you know that the Fourier transformation of impulse is what? Flat, right? So it is going to be that flat now. That's what I said. It is white noise. So this actually takes the complete range. In discrete, right, we normally plot between minus pi radian to plus pi radian. In fact, it gets repeated once again. So anyhow, it is going to be flat only, right? So in after taking discrete time Fourier transformation of this impulse, we get this flat. This is what we call it as white noise. So in time domain, this is the characteristics, right? So what is that characteristics explicitly? If you want to write, Rw of 0 is going to be, or I'll put it as k only, of k equal to 1 for k equal to 0, 0 otherwise. Okay, so this is what? The autocorrelation function of a white noise, and spectral density is constant throughout, right? So these two are the characteristics of this Wn, right? You have the filter here having 3 coefficients, and your Xn cap and the Yn, what is input to this filter, they are related. They are related, right? And we discussed that they are related in mean square sense, right? So let me write that expression here. The output of this filter is Xn cap, right? So that is equal to, in fact, above that equal to, I have to put MSS, because it is getting converged in mean square sense. I think this one I discussed in the previous class. You can see to the previous video to understand about that. So xn cap is what? Xn cap is you are doing a convolution. We have only 3 tab. So let me put 0 to 2 here. And here I am writing h of k because it is deterministic here. I am writing h of k in this, right? Y n minus k, right? So it is the regular convolution expression only, but remember that this is the deterministic coefficient, and then you have here random variable obtained from the random process, and this is the random variable obtained from the random process, right? They are related like this, right? Our goal is this expectation of xn minus xn cap, the whole square, right? That you are interested in minimizing that. This implies expectation of xn minus, I just expand this, you get this h of 0 yn minus h of 1 yn minus 1 minus h of 2 yn minus 2, right? The whole square. So this is what you are trying to minimize, right? So now what is unknown to you in this? The unknowns are h of 0, h of 1 and h of 2. They are all the unknown things, right? So you can actually differentiate this expression. This is that expression A. You have to differentiate with respect to what? The unknown factor, right? Like for example, h of 0, because that is what we don't know, right? You have to differentiate this one because I just wanted to minimize. If I want to minimize this, I have to differentiate this one with respect to h of 0 and solve for it, right? So if I differentiate with respect to h of 0, what actually you get? You get 2 times xn minus h of 0 yn minus h of 1 yn minus 1 minus h of 2 yn minus 2, fine. And then coefficient of h of 0, which is basically minus yn. So that I am going to write it here. Okay. Now this is equal to 0. This is the first equation what we are getting, right? So now you are going to have, you can expand it as it is equated to 0. This is not a issue, that's constant, that we can leave it actually. So one by one we'll do that, first term, second term and so on. First term is expectation of xn, and here we have this yn. In fact, I just remove this negative also in this negative and this constant because this is equated to 0, right? So I'll take xn and yn alone, right? This is the first term. The second term is h of 0, expectation of yn, right? And then minus h of 1, expectation of yn minus 1, yn, and then minus h of 2, expectation of yn minus 2, yn, right? So that is equal to what? 0. So this is the way how we equate. So now, because that we assumed that it is Whiteson stationary random process, right? And of course, it is about 2 different random variable obtained from 2 different random processes. One is xn and yn, right? It is what we call as jointly Whiteson stationary random process. This is another characteristics. We are again, one more assumption is jointly Whiteson stationary random process. Within itself is Whiteson stationary random process, and we have a characteristics of what? Jointly Whiteson stationary random process. So with that assumption, right, we are able to write this one as gamma xy and the difference in the time instant, right? So that is going to be at 0 here and minus h of 0, and this is going to be our gamma y of 0, and this is because the difference in the time instant is 0 here, right? So this is h of 1 and this is gamma y of difference in the time instant in this n minus 1 minus n. So this is going to be minus 1 here, minus h of 2 sorry, gamma y of difference in the time instant, right? N minus 2 minus n, it is going to be minus 2 in this. So that is equal to 0. So this is what that first expression what we are getting, right? So this is the first expression. And then if I do this differentiation with respect to, so I will write this expression here before that, gamma xy of 0. So that is equal to h of 0 gamma y of 0 plus h of 1 gamma y of minus 1 and plus h of 2 gamma y of minus 2, right? This is one expression. In the same fashion, if I do this task, right, by differentiating with respect to h of 1, right? So whole thing will be the same here. There is no difference. Only thing is this place it is going to be different, right? We have to write the coefficient of what? H of 1, so which is minus yn minus 1. So that is the only difference what we get in this. So if you do that, so what is that you get? In place of yn everywhere, it is going to be yn minus 1. That is a change actually you get, right? So everywhere I change, I will write it in a different color, right? In place of yn, you are going to have this yn minus 1 in every place, right? So here and here. So that is a change actually you get in this, right? So if I do so, what actually you get is gamma x y of, n minus 1. So that is gamma x y of 1 here. So that is equal to h of 0. The same h of 0 will come into picture, but gamma y of 1 will come because n minus 1 is 1 here, plus h of 1 and gamma y of 0 will come, and then h of 2 gamma y of minus 1 will come into picture. In the same fashion, if I do it for after differentiating with respect to 2 here, so if I do that, this one, right, do that differentiation with respect to h of 2, this will become 2 here, and everywhere it is going to be 2, it is going to get replaced with 2. That is a change in this expression. 2 here and then 2 here. We have a slight change in that expression, that h of 0 gamma y of 2 will come, and then h of 1 gamma y of will come, and then h of 2 gamma y of 0 will come, right, in this picture, right? So now this can be written in the form of matrix. I can write a matrix form, y of 0 gamma y of minus 1 gamma y of minus 8, and this is gamma y of 1, and this is gamma y of 0. And what is not known to you is your h of 0, h of 1, and h of 2, right? So that is equated to your gamma x y of 0, gamma x y of 1, then gamma x y of 2, right? This is very popular equation which we call it as Wiener-Hopf equation. Right? And if I solve this, if I know these values, and this is the cross correlation because it's a correlation of y with itself. This is a correlation between x and y. If I know that, then actually you can solve for this h of 0, h of 1, and h of 2. And hence your FIR Wiener filter is ready. We will stop here. We'll continue the remaining things in the next class, right?